In today's lecture, we're going to discuss the voltammetric detection modes that are used to decrease the charging current or the non-Faradaic current and enhance, your signal to noise ratio. Now, remember, almost every analytical technique out there, the goal is actually to lower its limit of detection. And for that reason, you've got these pulse voltammetric techniques, that have been used and experimented on and found, to very significantly increase the sensitivity and enhance, your signal to noise ratio, and of course, decrease, your limit of detection, which is a favorable figure of merit, when you're doing analytical chemistry. And as I said, the goal is actually to reduce the charging current, and that was the basis by which these pulse voltammetric techniques were developed. Now, the two that I'm gonna mention about or talk about is gonna be the normal, or what you call the square pulse voltammetry, and the differential pulse voltammetry. And as you're gonna see, they're actually very, very similar. The only difference, is just the architecture by which, you apply or the amplitude, to which you apply the voltages as you increase the voltages over time. So in this case, you've got, the differential pulse voltammetry, where you linearly, increase the voltage over time, but at set time intervals, you apply an amplitude where you radically increase the potential, and then you sort of you sort of bring it into a plateau, but in a slanted form, almost like a slanted staircase, and then after that, you drop it down, to lower voltage that's slightly higher, than the previous voltage at which you applied the initial amplitude. And on you go as you increase the staircases that way. Now take note of this, when you're doing the analytical detection, you detect, the current at S1, all right? And remember, that is a point, at which your charging current is actually fairly high, because you've just applied a potential, and the moment you apply a potential, almost right away, the migration takes place. Think of that as an electrode. Maybe I apply a negative potential of, say, minus 1V. Now, you're gonna see that all I've got, cations in this environment. The cations very quickly, get attracted to the negatively charged, electrode. And for that reason, you developed, this thing we are calling the non-Faradaic or the charging current. And so that's why I'm insisting, at this point, that's when your charging current, is quite substantial, because you've just applied, a potential, and the migration has taken place. So you record, the signal or the current, at that point, and then you apply an amplitude, and then you let that amplitude or the voltage plateau off, and then again, you measure, the current, at that point. So it's expected, in the S2, you're gonna have a bit of your charging current, but so also are you gonna have a bit of your Faradaic current, that is resulting from the redox process, within the electrochemical cell. And so if you take the S2 subtracted, by the S1, then you get this thing that we are calling the delta I, which is a delta current, which would be proportionate sort of, to the redox process, that took place. As I mentioned, in the S1, in the voltage S1, that is where most of the charging current is, voltage S2, you have a bit of charging current, but also the Faraday current that resulted from the redox process. And the difference between the two sort of negates, most of the charging current. And that becomes sort of your analytical signal. Now, one other huge advantage, of doing differential pause, and you can see it's very similar to the square wave. The only difference with the square wave is instead of having, this slanted, voltage plateau before the S2, in this case, you just have, a flat staircase. So that's the only difference. Otherwise, the points at which you do the measurement of the current, the S1 and the S2 is exactly the same. And then the difference between the S2 and the S1 becomes your signal, that you're actually detecting. Now, one huge advantage, of the type of signal profile that you get is the fact that compared to the linear voltammetry, where you get a sigmoid curve similar to a titration curve. Now, in this case, with the pulse voltammetry, you actually get instead a peak, all right? And anytime you've got a peak, that is a very good analytical signal, because it's fairly easy, to do integration. It's fairly easy to do integration of a peak, compared, to when you've got a sigmoid, type of situation. Now, as you can see, with these pulse voltammetric techniques, one huge advantage, as I've mentioned before, is that it decreases the limit of detection from by sometimes, more than 100 to 1,000 times, compared to other types of voltammetry. So that's a huge advantage of it. Meaning you can actually detect things, nearly in the nanomolar range, which is simply excellent. Now, another technique that I'm gonna quickly talk about is the anodic, stripping voltammetry, and I think I mentioned it previously. And the anodic stripping voltammetry is very prevalently used if at all you're dealing with very low, concentrations, of your analyte. Okay. So it's actually used, for what you refer to as a trace analysis. All right. So if at all you're doing an environmental type of analysis out there and you think probably you're dealing with very, very low concentrations of the analytes, which is often the case, you might consider techniques, that allow you to do pre-concentration, of a sample, and then you do the detection. Now, I don't know if you guys remember this, but if you think about chromatography, one pre-concentration approach, is what you call the solid phase extraction, okay? Now, in voltammetry, you can do something similar, in as far as pre-concentration is concerned, and that is only possible when you're doing anodic stripping voltammetry. Again, the purpose of it, is to electroplate, the analyte on the electrode surface, and that is pre-concentration, and then you strip it away, and then now when you're stripping it away, you're doing detection. Let me illustrate it, using, sort of, the time potential profile and the signal, potential profile that you would get when you're doing anodic. And of course, there's no reason why you cannot do cathodic, cathodic stripping voltammetry as well. You can do anodic or cathodic stripping voltammetry. Okay. Now, typically, you would take, your electrode, put it in the electrochemical cell. That is a working electrode. Of course, you still need your reference electrode, probably the silver chloride. And you, of course, also need a counter electrode. Typically, we use platinum. Now, you would apply a potential that is fixed initially. So you can see initially you apply on the electrochemical cell a high potential, such as -1 V, okay? Now, if you're dealing with cadmium, for example, that's what you're trying to analyze, say in wastewater. If you look at the reduction potential of potassium, and you can check, it's around, minus zero point 0.5 thereabout. Meaning, if I apply a potential of minus 1V, all the cadmium, get reduced. So the cadmium 2 plus, get reduced. So 2 electrons, to give me the cadmium metal, okay, at the deposition stage, when I'm applying a voltage of minus 1V, okay. So you can see that reaction actually takes place, at the deposition stage where I'm fixing the voltage, at minus 1V, which is often actually referred to as a deposition voltage. Now, when I get the cadmium metal, chances are the cadmium metal is actually gonna get coated, it's gonna get coated, on the electrode surface. If at all I'm dealing with very low concentrations of cadmium, the only thing that I really need to do is to increase the amount of time that I allow deposition to actually take place. So it's time dependent. So it's almost like I'm doing really chemical equilibrium, giving it enough time, for cadmium metal to be formed from this reduction process, and then it gets coated, on the electrode surface. Now, after that, I can change now my potential and start increasing it, from minus 1V, to probably, 0, V, okay? And so in that case, what would be happening is the reverse of reduction starts to happen, where the cadmium metal that was already coated, onto my electrode surface, now starts being oxidized back to the cadmium 2 plus, plus the 2 electrons. And at this time, that's what we are saying, we are stripping it, because of course cadmium is a solid, meaning it's going to get coated on the electrode surface. When I start oxidizing it, it becomes cadmium 2 plus. Ions are soluble in water, so I'm pushing it back to the electrolyte solution. And as I'm doing that, I'm measuring, my current, using, my potentiometry, using my potentiostat, so I'm detecting, the anodic current that is resulting, from the oxidation process, when I'm actually doing the stripping. And in the end, you can see I actually get, the peaks, that I can actually integrate, to determine the amount of cadmium that is present. So as you can see, it's a perfect way of doing pre-concentration. Very, very important, when you're doing trace analysis to actually do deposition, and then the stripping technique. So the last technique, type of photometry that I'm gonna talk about, is a cyclic photometry. And I think I already mentioned this in terms of the voltage time profile. It's a situation like this where I'm increasing my voltage linearly up to a point, maybe minus 1 to plus 1V. And then after that, I sweep it back from plus 1V back to minus 1V. And as you can see, the type of signal you get, is very similar, to a linear photometer, where you get the sigmoid when you're doing the oxidation, when you're doing the oxidation. And then after that, when you're doing the opposite sweeping, you get, sort of the reverse, of the sigmoid that you initially got. And that's why you're arriving at this thing that you call the cyclic photometer. Now, as you can see, a huge advantage of cyclic photometry is that you are able to monitor both cathodic processes or redox processes. So you've got, a cathodic peak right there. And also you've got, the anodic peak right there. So you've got more information compared to what you had before. And as such, cyclic photometry is such an important technique when you're trying to probe redox mechanisms, of reactions, because you're doing reduction and oxidation, at the same time. So it's actually a great technique, for analysis of nanomaterials, characterization of nanomaterials out there that are used especially for making energy devices. So it's a very important technique, for characterization of nanomaterials, for energy devices, because, you're probing both the redox, mechanisms, that are taking place, the oxidation, as well as the reduction. Again, the reduction here is what you refer to as the anodic peak, and this is what you refer to as the cathodic peak. And I don't have to ever emphasize this. Again, it's very, very similar, to a linear profile. It's only that you're doing it in, simultaneously, linear increase, linear decrease, and that way you get, the two sort of sides, of the redox processes. Okay. Now, it's very important, though, to remember not every analyte there is reversible. You can have a situation where an analyte, can be oxidized to give you a cathodic peak. You see, in this case, really, I do not have an anodic peak. And it becomes, again, a very important way to characterize, the nature of your analyte, whether it's actually a reversible process. So if at all I've got a situation like this, which is what I've drawn right here, you can see this one is a reversible process, meaning oxidation is happening. And after I oxidize something, I can equally reduce it in this case. So it's actually a reversible process. In some cases, you can oxidize something, but you're not able to actually reduce it at all. And that's common actually with lots of different types of antioxidants, such as ascorbic acid. Chances are when you run a CV of something like an ascorbic acid, you get a situation, like that, where you don't really have, a reduction peak. Meaning you're consuming, the analyte immediately when you do oxidation. So you're going to see one type of analyte out there that is used actually, to characterize electrodes, to check how nicely they are doing the electron transfer, is this thing that is called, ferricyanide. Because ferricyanide is perfectly reversible, meaning, the ion can be oxidized, to iron 3+, and then the iron 3+, can be reduced back, to the iron 2+, thus giving you the two sides of the peak right there, from the redox, from oxidation, and from the reduction as well. So actually this one is what people refer to as the redox couple. Redox couple meaning is a reversible process. And so, as I said, iron ferricyanide here, ferricyanide is actually used, to probe, a new electrode system, to confirm, that the electron transfer is fairly good, because you can monitor both the oxidation, as well as, the reduction as well. Now, other than just characterization, remember, you can also use it, really as a sensor, so you can use it as a way of quantitative, analysis as well. And that's what most of you are doing, in the lab, where you're using it, as a quantitative tool. And as a quantitative tool, you can monitor either, the cathodic peak. Remember this? Typically you would average, a range of your voltages here. You'd average the signal, that you're getting, the current, in a wide range, of your voltages, okay? Because of course the peaks, are often fairly broad, right? So you would take, maybe a certain voltage here, where the current starts to increase, and then the E2 here, and the current decreases. Essentially, you're mapping the voltage range, where you're getting, the peak, the current peak, the peak current, and then you can get, you can average, the currents, in that range, and that becomes sort of the signal, that you actually plot for your calibrations, and so on. I'm just trying to remind you here, about the parameters that affect your signal. Remember, your signal is a current right there. And all these parameters, actually affect, your signal. And electrode area, the nature of the electrode is a big one. Ideally, you want a very high surface area, that affords, the electron transfer, which is what you're trying to monitor. So the way you improve signal is, by increasing the surface area of the electrode. And that is why out there, a huge area of chemistry is actually a way to modify the electrodes, so that they can be very, very responsive. And sort of that's what you're doing in the lab, most of you, for your research projects. Of course, current is also proportional to the concentration. Of course, that's what you're interested in. Also remember this, and this is important, that current that you get is proportional to the square root, of the scan rate. So as the scan rate increases, sort of, your current equally increases as well. That's why you need to fix, your scan rate. For example, most of you in the lab are using 0.1 volts, per second, and then you fix it at that. Lastly, the diffusion coefficient, of your analyte. And I said that, I think a couple of slides before. The higher the diffusion coefficient, meaning the quicker, the mobility of that analyte towards the electrode surface, equally you get a high current, because current really is dependent on the migration, on the diffusibility, of the analyte to the electrode surface. So please take note of those parameters that you really need to optimize, when you're doing photometry in general and cyclic photometry specifically. For that reason, especially, the nature of the electrode surface and the electrode surface area, lots of people, are working on making microelectrodes, ultra microelectrodes, because as I mentioned to you guys earlier, small electrodes typically have got a high surface area to volume ratio. And that's the nature of any nanoparticle out there, or something that is very, very small. Typically, even particles that are very, very small, say 1 nanometer particle, in general, it would have a higher surface area, compared to a 1 micron, particle. All right. Often they have a higher surface area, to volume ratio, which we try to make use of, when you are doing electrochemistry. So miniaturization can be a very good thing, all right? Yeah, meaning sometimes smaller is better, actually. And that is the nature, of electrochemistry, that the smaller the electrode often, the higher the surface area. And as such, it gives you a very good, signal as well. And that explains to you why we are doing micro electrodes, for example, the microneedle, type of electrochemistry that I've been trying to indoctrinate you in, or introduce you to, for your research projects. Another important thing, with the small electrodes is that they've got fairly low charging current, which, as I've said before, is a big problem in photometry. Charging current is noise, okay? Charging current is noise. If there's any way of reducing noise, like we talked about pulse photometry, is a good thing. And it's been determined that actually small electrodes actually give you less charging current, again, which increases your signal to noise ratio, which decreases, your limit of detection, which is a good thing. But another huge advantage I should mention of miniaturization is the fact that you can do analysis in vivo. Meaning, I can take maybe my electrode, even a fiber, like fiber electrodes, insert it, possibly into biological specimens. And that way you can do actually the chemistry, in vivo, without being invasive, to the object or to the organism, that you are actually working on. So it's actually a very good technique in the sense that you can actually do diagnostics without being very invasive. So let me finish, by very quickly highlighting or, really repeating what I've already said, applications of cyclic photometry. As I mentioned, it's a good quantitative tool. You can use it for quantitative analysis. And you guys are doing that already in the lab anyway. So any redox analyte out there, or any analyte that is electroactive, you can actually use cyclic photometry to probe it quantitatively. As I said, also is a surface technique, meaning it's a great technique, to study the redox processes of materials of interest. And you heard me talk about energy devices. And of course, in the days that we are living in with the climate change, there's a lot of emphasis, to develop energy devices, small energy devices. And energy devices, lithium batteries, and so on. What you have there really is electrochemistry, is electrodes, that are being used. And people are trying to develop new electrodes, and they study those electrodes, using cyclic photometry so that you can understand, the nature of the electricity transfer, within those electrodes. And so CV is really used, to study the kinetics of electron transfer or electricity really transfer, being a surface technique. As I said before, people are trying to play a lot, with the solid state chemistry, so that they can make chemically modified electrodes. And that's what you guys, again, are doing in the lab, like you, Brittany, trying to work on a modified electrode, for example, that can generate hydrogen peroxide, or even that can detect, hydrogen peroxide, and others doing antioxidants, like you, Ashley, doing things like phosphates detection, nitrates detection. Again, some of you in class are doing that as well. So again, you can see, the vast array, of applications, of photometry and cyclic photometry specifically. And of course, there's no reason why we should not have used, things like the differential pulse photometry. There's no reason why we shouldn't have used square wave photometry and so on. But of course, we don't have enough time in the lab, to play with every bit of those techniques. But, hopefully you guys see there's wide array, of applications of photometry. And I think as I tried to show you, as I was doing my explanations and so on, you can see types of CVs, that is a redox process, meaning there's oxidation, and meaning it's a reversible, it's a reversible process. I'm able to do oxidation, I'm able to do reduction. But you can see in some cases, like in this case, I'm not able to regenerate, what I've oxidized. After I do the oxidation, I'm not able to get it. And that again gives you a lot of information on the nature of chemical species, that you're working with. So be able at the very least, to make sense, out of the CVs, whether qualitative, like what I just explained, or quantitative, like what you guys are doing in the lab. So a quick summary of all what we've talked about. Photometry in general, very, very important technique. It's based on concentration polarization. You are not waiting for equilibrium to take place. It's diffusion dependent. And typically you use a 3-electrode system comprising your sensor, which is a working electrode, your counter electrode, often it is platinum, and electricity or current, is moving between, the working electrode and the auxiliary electrode, and then you've got the reference electrode that is at fixed potential, and so the potential is fixed, between the working and the reference electrode. We talked about amperometry, where you're measuring the current at fixed potential. And we talked about, things like glucose sensors and so on, that are based on amperometric detection. We also talked about, voltammetry, which came from polarography, and polarography just meant that you are using a dropping mercury electrode, but these days we barely use a lot of polarography because of the disadvantages of dealing with mercury, although there are lots of previous advantages of using mercury in the sense that you can get a very good potential range in the negative range. It's got a very good reduction of a potential, meaning it's very clean in the negative voltage range. But in the positive voltage range, again, it tends to be messy because mercury tends to be oxidized as well. Now, we also talked about stripping voltammetry. Please pay attention to that. Stripping voltammetry, very, very good when you're doing trace analysis. Why? You can do pre-concentration. And lastly, we talked about, the cyclic voltammetry and how it can be used not only quantitatively, but also qualitatively to characterize different types of electrode nanomaterials out there. And of course, we also talked about, the pulse photometric techniques, the square wave photometry, and the differential pulse photometry that equally tends to increase, the sensitivity because of the reduction of the charging current. And so that brings us to the end, of electrochemistry. And then possibly, next week, be on the lookout. I think I'm going to post a few questions, just to make sure that you understand the content so that you can go through them as a small sort of multiple choice assignment, for comprehension purposes. So be on the lookout for that. Just a few questions, 10 questions, multiple choice questions to help you out.